Hello everyone, my name is Qiuna Zhang. I'm a PhD student from Harbin Institute of Technology, and I'm very glad to have this opportunity to attend the conference. The topic of my presentation is momentum-based adversarial attacks against end-to-end communication systems. My presentation will include these 5 parts. First, the motivation of our research. Second, the system model we have used in our work. Third, the generation algorithm of adversarial perturbation based on momentum we have proposed. Then, numerical results on proposed momentum-based adversarial attacks against end-to-end communication systems. And the last, some conclusions we have got. In the first part, I would like to introduce the background and the motivation of our research. With the development of wireless communication technology, the 5G and beyond have the growing demands, such as high reliability, ultra-high capacity, and low latency. Deep learning has powerful nonlinear approximation and optimization capabilities, which make it possible to satisfy the growing demands of 5G. For deep learning method used in wireless communication, one of the most novel concepts is an end-to-end communication system. It is based on an autoencoder framework in order to implement end-to-end optimization compared with conventional block-separated schemes. However, deep neural networks are extremely successful to adversarial examples. These examples can fool classifiers. The adversarial attack can be divided as white box and black box attacks, and it adds small and human imperceptible perturbations to legitimate examples. Compared with conventional jamming attacks, adversarial attacks are more destructive and unnoticeable because they are essentially optimization vectors deliberately crafted in feature space, which can change the optimization of loss gradient in wrong direction. For the end-to-end communication system, owing to the openness of wireless communication channel, an illegitimate attacker can add a small perturbation to the transmitted signal when it passes through the channel, thus confuses the receiver to raise security and robustness concern. Therefore, for the deep learning-based communication system, it is necessary to conduct further research from the perspective of adversarial attacks, since it inspires the studies of defined methods as well as the robustness assessment. For the deep learning-based communication system, one-step gradient-based perturbation generative algorithm have been adopted to corrupt white box and black box attacks. It can generate more transferable adversarial examples. However, these examples usually have a low success rate for attacking white box models. Therefore, we consider applying momentum into adversarial attacks, aiming to improve the effectiveness without losing their transferability. Now, we come to the second part. I would like to introduce the system model in our paper. Here, we consider a deep learning-based communication system consisting of transmitter, channel, and receiver, just shown in Figure 1. And the end-to-end communication system is that all its transmitter, channel, and receiver are composed of deep neural networks. This system tries to learn the channel characteristics mapped from the transmitter to the receiver, including noise jamming, fading, and distortion, so that the message sent by the transmitter can be recovered at the receiver side with minimum error rate. Corresponding to the components of the autoencoder, the transmitter and the receiver are represented by the encoder and decoder. In this system, K-bit message first passes through the transmitter to the channel, where it may be attacked by the illegitimate attackers using adversarial attack method, and then the receiver tries to recover it. Before input to the encoder, the message needs to be represented as a one-hot vector. And the last layer of the encoder is a normalization layer to ensure the power constraint. When X is transmitted to the wireless channel, it may face various channel environments. In this work, we consider the AWGN channel realized by a noise layer, in which attackers could craft adversarial perturbations to attack X. Therefore, the output of the signal, Y, is given by equation 1. After the channel, the receiver tries to generate a reconstructed message as height from Y. The last layer of the decoder is softmax activation operation, and as height is the index of the highest probability element in the probability vector B. To express the reconstruction problem of communication message as a classification mission, the cross-entropy loss function is adopted to optimize the distance between S and B, which is written as equation 2. Generally, block average P is used to measure the performance of the deep learning-based communication systems, justified as equation 3. Okay, now we move to the part of proposed algorithm. In order to generate a targeted adversarial example based on a real example, it should be constrained by LP norm within accuracy epsilon to make sure the adversarial attack is unnoticeable. Therefore, the gradient-based methods solving the optimization problem, like equation 4. Using the accumulation gradient of all previous steps to substitute current gradient, we can extend it to its momentum gradient variance. However, in wireless communication, L2 norm seems to be a more appropriate choice, since it usually represents the power of the perturbation. For targeted attacks, to seek an adversarial perturbation subjected to L2 distance, the update progress incorporates accumulated gradient of all previous steps into current gradient, which can be written as equation 5, where mu is the DC factor. Jt-1 denotes the accumulated gradient up to the current iteration. Y target is defined as the targeted misclassification label. R is the step size. So the targeted momentum-based iteration gradient with the L2 norm constrained just as equation 6. In order to evaluate the robustness, we propose a momentum-based adversarial attack method against the end-to-end communication systems. It can force the receiver achieve superior increasing of block error rate. Algorithm 1 presents how to generate an adversarial perturbation based on the momentum gradient. In algorithm 1, we use bisection search to find an appropriate value of the step size R among all possible targeted categories. Furthermore, for a specific target class, the momentum-based algorithm tries to minimize the loss function of xt star and y target, and then use the bisection search to find the appropriate gradient of t iteration with momentum. And the structure of autoencoder we use in the end-to-end communication system are multi-layer perceptron (MLP) and convolutional neural networks (CNN), whose structure and dimension are shown in Table 1 and Table 2. For the hyperparameters of our proposed algorithm, we set the descriptor mu to 1 and the number of iterations t to 20. In Figure 2, the curve of block error rates with different values of mu does not change much, but it can achieve stable performance when mu equals to 1 for different network structures. So we choose mu equals to 1 as one of our hyperparameters, which means we simply add up all gradients of previous iterations to update the current gradient. We also evaluate the block error rates of the number of iterations in Figure 3. And from the results of simulation, it is obviously that when t equals 20, the block error rates of different network structures are better than others. So we choose t equals 20 as the value of another hyperparameter. Then we move to the part of results of simulation. We first craft a white box adversarial attack with momentum. In a white box attack, we assume the attacker has full knowledge of the autoencoder, including the network structure and the parameters. We compare the performance of the proposed momentum-based attacks with jamming attacks for different networks in Figure 4 and Figure 5. We adopt perturbation to signal ratio, abbreviated as PSR, as metric, which is the power ratio of the received perturbation to the received signal. The value of PSR we selected are -2 decibel, -6 decibel, and -10 decibel. Figure 4 and Figure 5 illustrate that the proposed momentum-based attacks are more destructive than conventional jamming attacks, even for small PSR values, and the performance advantages are becoming more obvious as SNR increases. Secondly, we compare the performance of the proposed momentum-based methods with the method without momentum in Figure 6. It can be seen that the performance of the proposed algorithm is significantly better than the benchmark algorithm. This is due to the momentum-based algorithm accumulates the gradient of the loss function to achieve stabilized optimization and get rid of poor local minima and settle points. For verifying the transferability, we also craft black box attacks for the proposed momentum-based attack and the benchmark without momentum. While in a black box attack, the attacker has no knowledge or limited knowledge of the autoencoder. We first use the MLP autoencoder as the substitute model to obtain shift invariant perturbations, of course, based on momentum. We then attack the CNN autoencoder, whose structure and parameters are unknown for the attackers. We use the black box attack without momentum as a comparison, and the block error rates performance are present in Figure 7. So, comprehensively considering the effect of the white box and black box attacks, even the performance improvements of the momentum-based attacks in the black box attacks are not obvious enough. It can be concluded that the proposed momentum-based methods could increase the effectiveness of white box attacks and alleviate the cost of transferability at the same time. Now we come to the last part, conclusion. First, numerical results show that compared with conventional jamming attacks, the adversarial attacks based on momentum can effectively increase the block error rate for the deep learning-based communication models. Secondly, we also illustrated that the proposed method is more destructive than adversarial attacks without momentum accumulation. So we demonstrated that the adversarial attack incorporated with momentum can alleviate the trade-off between effectiveness and transferability of the adversarial perturbation. It is worth noting that our work addresses new security issues and robustness evaluation methods for building more reliable end-to-end communication systems. That's all for my presentation. If you have any questions, please feel free to contact me. Here is my email address. Thank you.